All right, so now let's take what we have learned thus far and combine it with a little relativity. I mean, because let's face it, this is why we study physics, is to do stuff like this. So, your reference frame matters. And this is true when you are observing fields. Okay, so let's set up a little scenario. You can have multicolored notes today. So suppose you are sitting, as you do, with a piece of charged tape. And a compass. So here you are, sitting, tape in hand, compass. And what you will see is you will see an electric field, and you will not see a magnetic field because you're sitting still and you need to move the charges to get that magnetic field. Now, your friend is running around. There they are, running, and they're also holding a compass. And they run by you. Now, from their perspective, it will appear to them as though you are moving and they are still, and they will see the electric field from the tape, and they will see a magnetic field because from their perspective, the electric field is moving relative to their observation point. So remember, magnetic field mu naught over 4 pi QV cross r hat over r squared. So if V is equal to 0, then the magnetic field is equal to 0. And if V is not 0, then you'd have a magnetic field not 0. So we can see perspective matters. Now you might be asking, well, then what do we use? Well, you observe from your own perspective. Which, when you do relativity, is a part of problem setup. And we'll see a little bit more relativity at the end of Physics 2, and we'll get to see a lot more in Physics 3. All right, so there are some interesting things that we can do now that we understand the magnetic field associated with moving charges. Namely, we can move towards understanding electron current, which is a whole bunch of moving charges. Now, previously when I have been talking about current, I was very careful to use electron in front of it, and we're going to see why now. So, one way to observe magnetic fields is to sustain moving charges. Like a current. All right, so we know how to do Biot-Savart, so let's apply Biot-Savart to a current of many electrons. After all, it's pretty rare that you're observing just one. All right, so we need an equation for electron current. So we would have our piece of wire with our positives in it. And you would have your applied electric field, which let's say it's going in this direction. Then your electrons would be going in the opposite direction. And for every negative, there corresponds a positive, which is generally how it works. So we want to make sure that we would keep these electrons moving, so we need to make sure that E net never drops to 0. And so what that means is there can be no excess charge on the wire. So in other words, we're going to keep this even ratio, or pretty close to even ratio, of positives and negatives. We don't have a charged wire that is running through current, and that's to keep it from polarizing. All right, so in any given chunk of the wire, the metal is neutral. So these are the setups that we need to start going after an equation. All right, so in order to get an equation, we need to assume current is evenly distributed. Now, we will go through in excruciating detail in the next chapter how to really understand current. It's a very conceptual chapter. It's often a favorite, but so if there's any fuzziness you feel thinking about it in this chapter, wait till the next chapter and then we can kind of address it at that point. Okay, so the distance an electron travels, or the distance the electrons travels, is described by V bar delta T. So you have meters per second times seconds, giving you just meters. And we can combine this with area to get a physical description. Because after all, we're going to move current through different types of wires. And so we need to bring that into our formulation. All right, so the total current, including area, in delta T is the area in meters squared times of the drift speed in meters per second times delta T. So we can think about it that this would be our area, surface area of electrons. We want to turn it into a volume because after all, currents go in three-dimensional space. So you would have your drift speed delta T to get the total part of that volume. And if we say N is the density of mobile electrons, which we have said before, then we would have N times the volume, which is N A V bar delta T, is equal to N A V bar delta T. So now we have a density, because we have electrons in that meters cubed, and now we want to get a rate. So then we just divide to get rate. We divide by delta T. So we have N A V bar delta T divided by delta T is equal to N A V bar. And so now we have our expression for our electron current, which I will rewrite. I is equal to NA V bar, where I is the rate of electrons that pass through a section of wire. N is the mobile electron density. A is the cross-sectional area. V bar is the average drift speed. And in SI units, units of I are electrons per second.